So, what's the reactivity we see? And since we got someone asking what was drawn there, I'll draw it a little bit bigger.
We have bromine and H2O and the alkene over on that ring.
So I heard we have bromine, we have H2O, and we have the alkene on the ring.
Yes.
I would argue you've made a couple shifts there within referencing. So if you're talking about bromine, H2O, and the alkene, saying bromine and H2O, you're referencing the entire molecule. When you said alkene, you're now referencing a very small part of that other molecule.
That's the part I'm focused on.
Okay, so that becomes an interesting differential and one that is worth exploring. If we're going to take a look at the organic molecule, hopefully what we see is that we have the alkene. We're looking at the pi bond. Those pi electrons are now going to be the most reactive thing, which means that molecule will act as what? Accept that. I'll even work with you and go with an electron giver. Typically we would say an electron donor, but that's fine. Okay. What things are electron givers?
Bases.
Okay, so we heard both our terms. We've got bases and we have nucleophiles. Okay. In the grand scheme, ideally, I want you to be able to find bases and nucleophiles. Okay? But as you suggested, the primary thing here is that it's donating electrons. It's an electron giver. Okay, so we don't have to know that that means bases and nucleophiles, but it can change our interpretation for the next question. If it's an electron giver, base, or nucleophile, what must it react with? Okay, an electron acceptor. Okay, so we would now need to move to our reactants to be like, is there an electron acceptor present?
Yes,
Okay.
no.
Before we get there, okay, what things are electron acceptors? Acids and electrophiles. Do you know what an acid is? Yeah, so if you know what an acid is, that can simplify your chemistry, and we can immediately look to those reagents and be like, do I see an acid? Okay, kind of, yeah. I'll work with that. What do you mean, kind of, yeah?
Something can donate hydrogens.
Something that can donate hydrogens. Can bromine donate hydrogens?
No, it doesn't have it.
No, which means?
H2O.
Water. Okay, so you're saying water can act as an acid. So when I step into the shower, I'm like, I'm melting.
No, that's like kind
Okay. While it has acid-base characteristics, it's not strong enough to act as an acid. Okay. So it has to be forced to act as an acid, which means if I'm going to make water act as an acid, I have to add a strong base, like hydroxide. Do I have a strong base?
of.
No, why not? What makes strong?
Charged?
Charge. Is my alkene charged? No. Okay. I could look at resonance to help me predict where that chemistry might be present, but it does not actually generate that charge because it's a non-polar covalent bond. This is why we want to be able to identify our bond types. Okay. So what does that mean? To it acting as an acid, or our starting material acting as our alkene acting as a base, that's not going to work because water is not a strong enough acid. Okay, so you did see an acid. Now we're left in kind of this weird gray area bucket, because if we don't have an acid, what does that mean we must need to find?
Weak acid, strong base.
Okay. Remember, we said our alkene acts as an electron giver, a base, or a nucleophile. If we know acid is off the table, is our alkene acting as a base? No. What must it be acting as? A nucleophile, or what's the other term that we've got written up there? An electron giver. Should have kept it as donor because we could keep reiterating it. Now everybody's going to memorize giver. Okay? So we've got the acid-base chemistry off the books. Now we have to move into either looking at electron acceptors or electrophiles. Okay? Either way you slice it, that's going to be challenging. How many times have we dealt with just electrophiles? Okay. At best, we've dealt with them this semester, that's it. How many times have you dealt with acids and bases?
A lot.
A lot. So you have a lot more experience within the acid-base realm, which means this next unit, or not this next unit, this chapter, becomes really challenging because it's now moving outside of your comfort zone into electrophiles and nucleophiles.
So what's stopping me from just really just connecting the H2O? Like taking that alkene, breaking it off, and connecting the positive end of the hydrogen, and then rearranging it.
What does that mean the water acts as? An acid.
Right.
Does water act as an acid? No. It can only be forced to act as an acid in the presence of a strong base. Is our alkene a strong base? No. So what's to stop you from doing it? All of that information we just said.
Memorization.
Okay? So we have to know something about the level of reactivity of our reagents. In that respect, is that memorization? Yeah?
Got it.
Okay. So knowing electrophiles doesn't necessarily help us yet. So maybe what helps us is if we move to the other statement, we want an electron. We have the electron giver. We need the electron acceptor. Okay? Okay? In looking for that electron taker, we could have pushed to the hydrogen. Why would we expect that hydrogen to be positively charged?
Because the oxygen pulls charge to it.
Awesome. The oxygen pulls those electrons away. And if we had run that reaction, so we'll call it blue, and right there you have all the evidence you need to know that it shouldn't work. You formed hydroxide. Is hydroxide more stable than where we started?
Okay.
No. Okay? That's now very, very reactive. That's a strong base. That's bucco danger. We don't want that. Okay? Is there anything else positive in water? That's a hard question. Yeah, the only other things would be positive would be the other hydrogen, which is going to reduce the same thing. Which means, what do we need to do?
Go with the bromine.
Go to the bromine. How would you expect bromine to react?
With H2O itself.
Just in general. We look at bromine. I look at bromine. How would you predict it to react?
On its own, just existing, I guess. I don't know. Just a nice even charge, both sides, nice even pool.
Okay. What do you see on bromine?
A lot of electrons.
Okay. And if you see a lot of electrons, what does that tend to make you think? Why is that problematic if we go back to our question? That's what the alkene acts as a nucleophile. So we have to be a little bit careful with looking at bromine as this big, oh, it's a nucleophile. Bromine is not a nucleophile. Bromide is. What's the difference between bromine and bromide?
Bromide's two.
Say it again?
It's two bromines.
And this may be a difference in emphasis, so we'll try it again. Bromine versus bromide. So that's N versus D.
Charge.
Bromide, based off of our nomenclature that we learned back in Gen Chem, yay, okay, is bromine in its ion form with a negative charge. That bromide should act as a nucleophile. Why? It's negatively charged. That makes a lot of sense. Okay? We're not looking at bromide, we're looking at bromine. How is that different? There's no charge. So to Adolfo's point, that's a nonpolar covalent bond, sharing of equal electrons and all that. Okay? And then this is where we have to push on that a little bit. And this can now start to move into expanding your horizons on the potential chemistries for our halogens as a whole. Okay? Is bromine electronegative? If we consider our halogens, do we consider our halogens to be electronegative? Yeah. Okay. They tend to be fairly electronegative. Okay. Not the most electronegative, but they tend to be electronegative. Okay, which means what are they both doing on the electrons in that bond? They're pulling on them. Okay? And officially, they're pulling on them equally. Okay? That bond isn't just going to break on its own. Something would have to cause it to break. Okay? There's a variety of ways that we can cause that bond to break. One of them is to saddle up an electron giver next to it. What happens if that electron giver gets near that bromine? What's that? What repels? What electrons? All the fun.
They all repel each other because they're electrons. The alkenes and the bromine.
The electrons in the bond between the bromines. What happens? We're going to form bromide, okay, negative charge, and we're going to leave the other one alone for the moment. For our blue reaction with the water, we said that one shouldn't form because we form hydroxide. And hydroxide being a strong base, that's unstable. We don't want to do that. What can you tell me about bromide?
Unstable.
It is charged. Is it unstable? No, it's actually incredibly stable. Okay? It's large. It's electronegative. All of those things contribute to its stability. Okay? Where can we push on that even further? HBr is what kind of an acid? It's a strong acid. Why? Because the conjugate base, bromide, is a weak base, ultimately because it is insanely stable. Bromide is very, very, very stable. Okay? So that reaction makes a whole lot more sense than running the acid-base path. Okay? And this does become tricky. This is something that will haunt you through second semester. When you see Br2, how does it react? What did it act as in the course of this reaction? You get 3 different answers. Leaving group is not referencing bromine. Bromide is a leaving group. I didn't ask about bromide with a D. I asked about bromine. What does bromine act as in this reaction? Say again? What do bases do? Accept what? Hydrogen. Did it accept a hydrogen? No. So it's not acting as a base. Try again. Okay. What happened? It accepted electrons. It is therefore an electrophile. What else could we have used instead of using our fancy terminology electrophile? An electron taker. Okay? So we can look to where those electrons are moving and how they are maneuvering to help us predict this chemistry. We don't have to use the terminology. Does the terminology come in handy? Yes, which is why I tell you you should memorize and learn that terminology, because we can manipulate it. But if you decide you're not there, then focus on the electron givers and takers. Okay? So cool. Every time you see Br2, you should say electron taker, because it took electrons in the course of the reaction, okay? Or it acted as an electrophile. Those are our 2 options. Okay? We're now going to encounter a realm of things that you need to memorize. Okay? We're talking about a positive thing that is not hydrogen. We dealt with positive things that were hydrogen. Those were acids. We're used to those. Hydrogen can form only one bond and everything's grand and happy within the world. But now what we're looking at is an atom that is not hydrogen. How can it potentially change and alter the chemistry? Some of this comes from actual experiment. So we don't know until it was actually tested. Once it was tested, we know the answer, and now that we know the answer, we have to backtrack an explanation for why that happened. If we go through and predict as we have drawn, what we should be drawing, hopefully, would be this, with the positive charge there. Everybody agree? Okay. Before we get too excited about drawing, that is wrong. Okay. So hold your breath. Don't hold your breath. I take too long. Okay. What would we predict happens? Okay. So this is now where we want to push on this a little bit. What can you tell me is special about the carbon where the bromine's connected?
Nothing stable.
A secondary. It's stable because it's not charged. Keep going. Is it what?
Chiral.
Chiral. What does chiral mean? It's bonded to 4 distinctly different things. Because it's bonded to 4 distinctly different things, we should be specifying the stereochemistry of that particular bond. Well, should it be wedged or dashed? Okay? It's going to be both. Why is it both? That's the hard question. Oh, Dad, you got it? Yes, depending on how the molecule flipped or turned, I agree. Do a little bit more. Can you push on that a little bit more? It's hard. What molecule do we care about? Okay, so here's an interesting point. We have 2 answers possible, and they both said different things. Unfortunately, Jazz is right. Yes, the alkene. It matters about the alkene. What about the alkene? Is it this part? No. Okay. Is it this part?
Yeah,
Why is it?
because that's the pi bond that we're removing.
That's the thing that reacted. Where are those electrons located? Between 2 carbons. Keep going. And arguably, actually not. Yeah, you're like, that doesn't make sense. You drew it between 2. I know. Where are those electrons located? They're located in p orbitals, above and below the carbons, not technically between them, they're above and below. Why is that important? If the electrons come out above to the bromine, the bond to the bromine is now up. If the electrons from that pi bond that are below come out to the bromine is now below. Dang, that's where the chirality comes in. How the electrons of the pi bond move out. And because the pi bond exists both above and below, I get 2 products. Okay, that's nasty. That means every time you run an addition reaction, what do you need to be concerned about? Stereochemistry. Okay, that doesn't mean it's a requirement, but it should be at the back of your mind because of this necessary system. And not only just stereochemistry, how many possible products? 2, because it can either go up or it can go down.
So, how's that wrong then?
I don't remember. When were you wrong?
You said that, like I said, that there's 2 ways that it goes on both ends, and those are the 2 correct ones. Pretty much.
Yes, the question just becomes why. I think that you were wrong for the why. Okay, so this should be wedged or dashed. We're not specifying it. Our fancy notation for that, what was our fancy notation for that? Anybody remember? It's okay. What the hell is not the appropriate response, but I get it. Okay, that was a little ziggy wiggly line. Okay, that's saying there's stereochemistry there, and I'm choosing not to reference it. Okay, generally we don't do that. Okay, if we care about stereochemistry, we're going to draw it. If we don't care about stereochemistry, we're not going to draw it. And those are our 2 options. Okay, in this case, I want you to be aware of it, so I'm going to make it look weird and a little bit nasty, so you're aware of it. Okay, it is the standard notation for this. Okay, so we've now expressed that there's 2 products of this one reaction, or really this one step. Is this our final product? No, this is technically just an intermediate. What has to happen? I have to get rid of the positive charge. What do I need to do to get rid of the positive charge? I need electrons. Where do I have electrons? Okay, cool. We're going to work with bromine for a second. We'll discuss why that's wrong in a little bit too. Okay, but we'll work with the bromine for the moment because it's useful to talk about it. So that bromine comes in. What's going to be special about the new product? Okay, we'll say bad down here just so we all know later.
Not charged.
It's not charged, yeah. What else is special about it?
Is it another squiggly line?
Is it another what?
Is it another squiggly line?
What do you mean? Why would it be a squiggly line? because it's... Is that a chiral carbon? Yes, it is. Okay, depending on which way we go around it, we're going to see 4 distinguishable groups. So that is indeed a chiral atom, which means we would then need to also be concerned about where that bromine is located. Was there evidence in our mechanism that told us that we needed to worry about that instead of just looking at the answer and being like, damn, I got to worry about chirality? What did the bromine react with? The carbocation. Okay, what was reactive about the carbocation? Be real specific. Way to be super, super specific, okay? I didn't think we were going to go there that fast. The positive charge is where I thought we were going to go. And then I was going to ask, where's the positive charge? And the positive charge is found on? Nope. You said it, so I thought you said it. Maybe you didn't. Where's the positive charge found? It's not on an alkene. That's over here. It's on a carbon. We already knew that. That's why we called it a carbocation. Where's the positive charge found on that carbon?
In the pi orbitals?
Right idea, wrong word. That's a pi bond.
I'm sorry, p orbital?
There we go. It's in a p orbital. And where's the p orbital?
Above and below.
Above and below. We get the exact same issue, which means this bromine could either come in to fill the electrons above or below. Okay? I'm just pretending that's a squiggly line. Why has this become important to us? Okay? The bottom bromine could be wedged or dashed. The top bromine could be wedged or dashed. Okay? Which means I could have wedge, or I could have wedge dashed,
What do you mean more stable though? Like,
or I can do dash wedged or dashed dashed. So I get 4 possible products. Deciding between those possible products, which might be where you're about to go into, whether they are unique or new or different from each other is a different question, and I actually don't really want to think about it because that involves all the chirality stuff that we didn't like anyway.
that's cool.
Okay, we good with that?
Yeah.
Okay, what was your question?
No, exactly that.
Okay, good.
Yeah. Isn't too more stable, but yeah.
Okay, so that would suggest 4 products. Okay, this is the experimental result that comes in and tells us our mechanism is flawed. The experimental result says I do not get wedge, and I do not get dash.
That makes sense.
Why?
Because electrons repel.
Yeah.
What electrons?
The electrons on the
This bromine is going into an empty p orbital. You're like, well, it's too close to this. It comes in from this side then.
Well, I mean, if they're both jutting out the same direction, it's not going to want to do that because they're still close to proximity.
So once I have the product,
Yeah.
there would be steric considerations.
Yeah.
That still says I have the product. This says I don't get the product, period. You're evaluating the situation once it is formed. It has never formed.
But that's explaining why something wouldn't form in the first place.
You're talking about the end result and saying, well, that thing's bad. There's something more important here that you're missing.
So what are we missing?
We get 2 results because this bromine could come in from the top or the bottom, right?
Yeah.
But if this is wedged, it can't come in from the top.
Right.
Why not? If bromine is big, then you're making the argument that wedge and wedge, once it's formed, is unstable. Again, you can't do that. Bromine being big is important. Really important. It's so important that it prevents the top of the carbocation from existing.
Right.
Well, if there's no top to the p orbital, is it a carbocation? A carbocation is an empty p orbital. I have a top lobe and a bottom lobe.
Yeah.
If I'm saying I don't have a top lobe, do I have a p orbital?
It's over there.
If there's no lobe there, you can't tell me that's a p orbital. P orbitals have a top and a bottom. Period. That's how they work. That's what p orbitals are. Quantum.
Okay.
If you're now telling me the top p orbital doesn't exist, that's not a p orbital anymore.
Why doesn't it exist?
It doesn't exist because I can't put the bromine in. If I define that bottom bromine as wedged, this other bromine here can never attack from the top. It can't attack from the top because there's no orbital there to place the electrons. And if there's no orbital there to place the electrons, it can't be a p orbital. Because a p orbital has a top and a bottom. If I get rid of the top, so what's left? What's that? Sort of. So here's a p orbital. We just said I can't have the top of that p orbital, right? That has to disappear. What would an s orbital look like?
A big circle.
So what orbital looks just like this? It's a little bit off.
So it's what, the red one or the blue one? Both.
What's that?
SP.
An sp orbital. An sp orbital where there's negligible presence of any orbital up top. That's an sp orbital. But if it's an sp orbital, can I draw it as a carbocation? No, because a carbocation requires a p orbital. So I have to theorize something that explains the lack of that orbital existing there, but I still get an orbital aimed down.
Does it work the same way, say if the other one was dashed, then the bottom doesn't exist?
If our green bond was dashed, then does the bottom not exist? Yeah, absolutely. Okay? Which is why when we look at this bottom, if we called it wedged, what must the top be? Dashed. If we called it dashed, what must the other one be? Wedged. And this is happening because that bromine is forming a bond there. Do you like that drawing? Why not? Okay, it's ugly. I'll beautify it a little bit.
Never done that before.
My definition of beautify versus your definition of beautify might be challengeable. There's my beautified version of it. Do you like that drawing? No. Why not? I've never seen it before. That's fair. Oh, shit, you have? Oh, well, have you watched all the lectures? Yeah. Okay.
I just don't understand it. Or I feel like charged.
That bromine is now charged. That bromine should be positively charged. Okay? Does bromine want to be positively charged? No, which means it's highly susceptible to a nucleophile coming in and attacking one of those two bonds. Okay? Either we'll call it the blue or the green. Right? Okay? Is one of those more likely to happen than the other?
The green, right? Because if the nucleophile has to come in from the back, all the electrons are already in the front, so it'd be more willing to.
This has a lot to do with leaving group ability here. Does the bromine want to leave? Yes. Why? It's positively charged. So it is effectively already leaving. If it is already leaving, what is it leaving behind? A positive charge. Where is my positive charge more stable?
In the blue one.
In the blue one. Which means my nucleophile is going to come in and attack the blue spot, not the green spot. I didn't say you were wrong. Maybe I didn't hear what you were saying. Okay? So the green one becomes the bad option and we instead see blue. Okay? So a lot has to do with bromine's ability to act as a leaving group. If bromine was a bad leaving group, what has to happen? If you've got someone in your house that's a bad guest, what do you have to do?
Kick them out.
You have to kick them out. Good guests leave on their own, right? I think that's right. Okay. Leave on. You don't have to kick them out. Bad guests, you got to throw them out. You got to be mean enough, big enough, strong enough to do that. Which means what kind of nucleophile would you need?
Strong.
a strong nucleophile to force it out. And if I use a strong nucleophile, is it easier to get in blue or green? Green. Ooh. I change the strength of my nucleophile and it changes where my reaction reacts. That's dangerous. We got to be real careful with that. Not something that's going to constantly appear with all of these electrophile addition reactions that we have to be considering and walking through. Okay? What else can we fix about our drawing? Because there's something else that's pretty important that we need to fix. We technically already addressed. What can you tell me about, we'll call it blue spot?
It's chiral.
It's chiral, which means
You have to worry about its stereochemistry.
I need to worry about the stereochemistry. Can you tell me where any of those bonds are? Whether they should be wedged, dashed, or solid.
Meaning with the one connected to the bromine need to be wedged.
Why does the one connected to the bromine have to be wedged?
It's connected to the wedge bond.
Okay. Your answer is probably the most appropriate and somewhat obnoxious. What's your answer? It's just the structure. You're forming a three-membered ring. If I'm saying one of them is up, how do I make the three-membered ring where the other bond is down? That's not going to happen. It has to be based off the structural relationship. You mean the cyclopropane forces that. Cyclopropane type structure forces it. Yes. That's exactly what happens. And if that's wedged, what does that mean our methyl is? That one becomes dashed. Now all of the stereochemistry necessarily follows out of it. So cool. We've fixed the end result, okay, because we now only see the mix, the wedge dash issues. Okay? Did we fix our mechanism? Does our mechanism show the formation of that? Adolfo with the sigh. No, it does not. Why does it not? That arrow shows the formation of the green bond. We break the bromide off. Great, that's not there. Where's the formation of the blue bond? It's not there. So what do I need to do?
Have another step.
Not another step. I need to add another arrow. I can't add another step because that's suggesting I form the carbocation. We just addressed we can't form the carbocation. I need another arrow. Okay? So that green bond formed with our bromine, and it immediately forms a bond back. Okay? Which means that structure, the thing that was attacked, had to both accept electrons and, nastily enough, give electrons. Ooh. Okay? That's very carefully looking at each of those individual steps through it. Do we encounter this in other scenarios? Yes. Okay? Which is why what we're trying to do is zero in on the characteristics of the piece, not the piece itself. Does that make sense?
Yeah.
In the description of the videos, what I'm referencing here is when my electrophile, the thing that's attacked by my alkene, has a good leaving group and a pair of electrons. If it satisfies that, what do I end up forming? This hellishly awful three-membered ring. Okay, why does that become important? This three-membered ring that needs to break apart. The nucleophile comes in and attacks, and the result that I get is wedge dash or dash wedge, right? What does that mean if I look at the overall reaction? I know I didn't cross it out. Okay, so let's draw a specific one here. There's a wedge. There's a dash. Okay. What kind of reaction did I do to go from my alkene to the dibromo? It's an addition. I lost the pi bond. Is there an SN2 along the way? Yes, don't worry about it. That's SN2 mechanism along the way. Okay. It's formally an addition. What happens in an addition reaction? Lost the pi bond. Cool. And?
Creation of 2 sigma.
The creation of 2 sigma. Where were those 2 sigma created?
Bromine. Opposite of each other.
Opposite of each other. So if I now want to classify this reagent, I can say that this reaction is going to run an addition reaction where the two sigma bonds that are added on opposite sides. That's a whole hell of a lot of words. So what do I say instead? Anti-addition. Okay? Probably makes sense to go through and say they're added on opposite sides instead of inventing new words. Okay? And for those of you who are really paying attention, it's anti-addition, right? That's what we said. Have we heard the word anti show up before?
Yeah.
Yeah. Is this the same anti? No. Be real careful. It's a different anti. Okay? So anti-Newman versus anti-addition, two separate things. Keep those categories separate. Okay? Kind of, sort of?
Sort of.
Okay? So we've walked through kind of the details behind what's happening here. We're finding all of our pieces. We're introducing our mechanistic detail behind it. Okay? But then Ivan would probably say, but Mike, I put that answer in and I got it wrong. You did. Okay? You did get it wrong. Okay? This first step, absolutely valid and awesome. So we're going to stick with that. Okay? But using the bromide as our nucleophile to come in and attack, that's the better place to attack because our current bromonium ion, the one with the positive bromine, okay, is a good leaving group. That's a bad reaction to happen. Why is that a bad reaction to happen? This sucks. It's a bad reaction to happen because the concentration of bromide is very low in comparison to another nucleophile. Water, as we addressed at the beginning, has electrons and could act as a nucleophile. Water is also going to compete. So we get reaction A or reaction B. As a hint, reaction B begins with B, which is bad, and reaction A begins with A, which is excellent.
You could have went with awesome. You just went.
Awesome. That would have been a better word, you know.
I think you just couldn't spell awesome, so you showed me that.
Did I spell excellent right, even if I made it an E?
Oh yeah.
Pretty good.
Okay. Would that be a final answer?
No.
Why not? Okay, so what should we do?
That's all electrons. Give hydrogen.
No big deal.
Make
Fine.
hydrogen plus.
I need something with a source of electrons to come in, remove the hydrogen, give our electrons back,
And I guess there's
which means the species that I'm adding is what?
a base.
A base. Note that that base that I'm adding is not a strong base, because a strong base is something that we would have called out as a reagent at the beginning, which we did not. So it's anything with electrons. What has electrons? Water has electrons, would be perfectly acceptable. Okay?
I'm just curious, and this may seem like a dumb question, but could the bromine take that hydrogen, theoretically?
Could you show the bromine taking it? Yes, and people would probably expect it or accept it, and I would argue smart work might even have the bromine pick it up. Would I suggest that's a good idea?
I presume no, based off your tone.
What would it produce?
Acid?
HBr. And what do I know about HBr? It's a strong acid. What do strong acids do? Dissociate. You break the bond. So showing me bromine picking that hydrogen up
It's just
doesn't
gonna
make
go
any
back.
sense. It's just going to go right back that same direction.
Okay, I see.
Okay. So do I care mechanistically enough that I would ever ask about? No. Okay. I would actually argue that if I had to draw a mechanism, that's all I would expect to see.
Cool.
Just something takes the hydrogen. I don't really care. The bond just breaks. Ta-da. There it goes. Okay.
Should the bond from carbon to oxygen be dashed?
Is that a stereocenter? Yeah, which means?
Yeah.
Do I need to specify stereochemistry?
Yeah.
Yeah. Where did the oxygen come in from?
The backside.
The backside, if the bromine was wedged, what must the oxygen be? Dashed. Is that a proper drawing?
Well, doesn't the CH3 have to be wedged then?
Now I need the CH3 to be wedged.
Do you
Okay.
need to dash the hydrogen that's next to the beer?
So there's a different, interesting question. Do you need to dash the hydrogen? No, but yes. Okay? No, you don't need to. Where are you getting this question from? Smart work. And what does smart work say for every chiral atom? Show all the bonds. So smart work gives you direction saying you must show it. So do you need to show it? Yes. Okay? You need to show it because smart work asked you to. You don't need to show it in any other scenario. Okay? For those people wondering why it asks you to, they need it so that they can assign stereochemistry appropriately and ensure that you're drawing the correct answer. Okay? So cool, you answered the question about the stereochemistry. I like that. So we could even double back here and we could adjust that. What did we say it was? We said it was dashed. Okay. Do you have any other questions you want to ask about it?
I had him, I lost it.
I would argue there's a huge, like, what the hell question.
Yeah.
Why did we say water react instead of bromide?
Higher concentration.
Where does it say anything about concentration?
It doesn't, but it's the solvent, so there's got to be a lot of it, right?
It doesn't, right? But there's an interesting follow-up. You're saying water is a solvent. Why do you know water is a solvent?
I just do. I mean,
It is, yeah.
it's under the arrow.
It's under the arrow. So that means every time you see this reaction, it's under the arrow?
Well, okay. You want to be the okay, I see.
It's underneath.
Okay? And I'm not saying you're wrong in your statements at all. But what I'm saying is that when we go through and look at this particular reaction, you could see it this way. You could see it with water under the arrow. In fact, that's typically how I'll show it. Bromine on top, water under the arrow. To provide some level of context behind it. You could just as easily see it Br2H2O
But
with maybe a comma in it.
we still know H2O.
Right. But you have to know that H2O in this context is the solvent for this chemical reaction. And because it is the solvent for this chemical reaction, what is its concentration? Really flipping high. So that when we look at the competition between bromide, where did it come from?
The solute.
Was bromide present at the beginning of this reaction?
Oh,
No. The bromide only came into existence once we started the reaction, which means the concentration of bromide is insanely tiny, minuscule. Which means if we look at this bad, I need to fix that. This bad versus, it was a good suggestion, versus awesome potential reaction, how do we differentiate that? Okay? Bromide is the better nucleophile, but its concentration is so low that water outcompetes it. How would you ever know that?
you draw it out.
Where do I say anything about concentration? Drawing it out doesn't necessarily help you figure this out. The only way you answer this question is by having done the experiment. Okay? And how do you do the experiment in lecture? You don't. You have to trust that someone has done it for you and is now telling you those end results on what happens. So you have to pull some of that information out of the context of your readings or the lectures. Is that easy to do? Hell no. I really despise reactions that involve concentration. Do they show up? Yes, this is a primary example for it. Radical reactions is also a primary area when we talk about concentrations. Because you can drastically change the output of a radical reaction by changing the concentration of your reagents. Yes, sir.
So you said bromine H2O is this whole solution that we're putting our
Alkene
Whatever.
into. Yep.
yeah, whatever it is. So my H2O and bromine are together first. So And from the start of this reaction, we only took alkene to connect to bromine, like as the first step. But wouldn't the first step be the H2 and the bromine together first?
So they're mixed. Do they form anything that's a product or an intermediate?
So would they just be completely like separated? Even in the solution, it would still be separated until I add that like alkene in there.
Let's just say I think you're splitting hairs, and at best you're going down a rabbit hole that isn't useful.
Okay.
Yeah, we can talk about it after class, but
Cool.
yeah, I think this reaction is painful enough. We don't need to keep beating it.
Yeah.
Kind of, sorta.
Sorta.
So that gets us one of the answers. Did you get the other answer right? Or the other question right? Because it did say 2 parts.
Yeah.
We'll clear all that. Okay. Figuring out your 2 products does become an important thing on their relationships. Because of how the dynamics in this reaction works, you end up getting enantiomers. Okay, one's wedge, one's dash, the other one's dash and wedge, those combinations. So when you run addition reactions, you almost always get 2 products. Hesitantly, you get enantiomers. Okay. Why hesitantly? If you memorize that, which is common, all we have to do is make a subtle adjustment to this. Does that change any of the enantiomer chemistry of our alkene? No. So all of that is still going to go through the same reaction, you're getting the same results, except does this stereocenter ever change? No. Which means while the chemistry here, this is going to be a little bit weird to say, but I'm going to say it anyway. While the chemistry here is going to produce enantiomers, the chemistry out here never changes its stereocenter, which means the end result of your products is not enantiomers, because this spot didn't change. Which means the end result is the relationship is, yeah, the diastereomers. Okay. Can you run addition reactions where you only get 1 product? Air quotes, yes. You're getting 2 products or 2 ways of making it, but it's the same structure to end with, which means you only get quote unquote 1 product. I would argue all addition reactions, you should assume 2 products. Now what's the relationship between those 2 products? If they're identical, you say it's 1. If they're not identical, you say it's 2 products.
In chapter 11, you said we go over acid and base, so it's a good way to, like, if we have these questions on our exam, to decipher them from, hey, we're going to go down a huge, complex question versus our acid base that we were dealing with earlier, is just focusing that we have an acid.
So I think the question that you're asking is that if you see this on your final, is this a question you should devote time to?
Kind of, yeah.
I don't know. Did you study it? No? Then don't spend any time on it.
Right, but like I said,
Okay.
so an easy way to like look at this would be like, hey, look, I see this H2 in the bromine tube is going to be complex versus if I see like a strong acid, it's like, hey, yeah, this would be a lot easier.
So yes. So in that respect, you can take this last unit and you can divide it into kind of 2 categories. I know my acid bases, and because we talked about addition reactions, I kind of know what's going on with addition reactions. I can overlay that with my acid base stuff. I can predict those products. I'm fine. Electrophiles, what the flipping hell is that? I'm going to ignore it. Okay. That means you'll pick up some of the new content. So this last unit, 15 to 20 questions, maybe. Okay. You'll get maybe 10 of them right, and 10 you can just toss out the window. To that kind of end, I wouldn't really fully toss it out the window.
Right.
What I would do,
Okay.
sort of, I think, is that in the last, week, So I think the exam is scheduled for Thursday. So starting maybe Monday, you're looking at these 3 slides. And all you're trying to do is memorize them. Okay. Those 3 slides aren't perfect. They have some information in there. They're also missing some information kind of by accident. A lot of that has to do with the material that you start with. Depending on what material you start with, some chemistry becomes obvious, some chemistry is not. Sometimes it was specified, sometimes it was not. So for instance, that's kind of ridiculously small. Let's make this a little bigger. And I was going to try and zoom in. For instance, if we look at this particular reaction right here, I would argue the answer provided there is misleading for multiple reasons. Number one, what kind of reaction did we do? An addition, which means how many products?
2.
2. Which of these reactions showed 2 products?
None.
Well, they say plus and hand.
Those 3 actually did. I thought none of them, but I happen to remember those. Are they going to be enantiomers? Look for other stereocenters that weren't involved in the chemical reaction. So they aren't necessarily enantiomers, but where the chemistry is happening, yes, you would get enantiomers. Okay. This red one looks suspiciously simple. All we do is add H and OH. Okay. Some things that become red flags on this. Where am I getting H and OH from? Those reagents look really weird. Okay. On top of which, if we're adding H and OH, where did I add the H and OH? Well, the OH is off obvious. Where's the H?
The other carbon.
This carbon? Just checking. The other alkene carbon over here. What's special about those 2 carbons? They're chiral. And if they're chiral, should I be showing stereochemistry? Yes. Okay. So we already addressed one of those kind of stereochemical situations. We got the anti-addition. This reaction is super commonly tested on because what do we get instead of the anti? Sin. You're like, sin's the opposite? I don't know where it came from either. Synthesis means same text. Yeah, because you're putting all the pieces together into one thing. There you go, sin. All the pieces come into the same side.
Wow, you are reaching.
I look it up. Actually, I think I'm actually probably pretty damn close. Yeah, it's a sin addition. Okay, that's how that one gets referenced. That one is very commonly tested because how often would you expect to see a sin addition? Not. You're putting electrons in on the same side? That doesn't make sense. Ta-da, it happened. Okay? That's why they tend to, what?
It's sinful.
I don't want to explore that one. You could also get them being dashed. Okay, where they're both dashed. So you do get 2 products here as well. Okay? What else is neat about this particular reaction? We talked about the addition reactions, right? The addition of hydrogens. Where do our hydrogens go?
Where the negative charge is.
Where would you predict the negative charge to be in our starting alkene?
Well, nowhere. I mean in the starting alkene, nowhere, but what do you?
Oh, once I move the alkene out?
Oh, that is fucky, huh? You would expect it to be on the secondary, huh?
Okay, reel it back in and clue in the rest of us here.
So, I mean, you'd expect the anion to be most stable on the secondary carbon, not the tertiary, right?
That's what we would expect for our resonance, which means the negative should react with the hydrogen at that spot. That's called Markovnikov addition. That's why it was named after him. Okay? This reaction places the hydrogen at the other spot. Damn, must be anti-Markovnikov. Hydrogen goes to the negative carbon because what charge is the hydrogen?
Positive.
Positive. What charge is the hydrogen in this chemical reaction?
Negative.
It's negative. Yeah. You're like, but hydrogen can't be negative. How did any atom become negative or positive?
I'm sure there was a lot.
Why is hydrogen positive in HCl?
Because chlorine pulls electrons.
Chlorine pulls the electrons away, so it's a different electronegativity, right? What if I make this a sodium? What's that?
Sodium just
Answer my question.
So the hydrogen pulls the electrons?
The hydrogen would take the electrons away because the sodium is a spectator ion, has very low electronegativity, becomes positive. So hydrogen can become negative. How reactive is sodium hydride? It's really, 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 really reactive.
Imagine that like
Okay.
blows up and put it in water.
Ish.
Finish.
It's less reactive than just dropping sodium in water. Where do the electrons in the bond go?
Wouldn't we go to the boron?
Why would they go to the boron?
I'm just guessing, I can't remember. Is it more electronegative? Can't find it.
So, and this becomes the fun part, is everybody go to look at the periodic table. The periodic table gives you what?
The flow or the
The general trends, not the answer, the trends.
Oh, then yeah, it would definitely take the
I'm
electrons.
trying to look boron still, yeah.
It most likely will take it.
Hydrogen's more electronegative than boron.
What?
Well, I mean,
That's why hydrogen carries the negative.
so much for a trend, huh?
So one of the things with that trend that you do got to be careful with, hydrogen is fun and floats off the periodic table. Arguably, you can place hydrogen right above fluorine.
What do you mean above
Right above fluorine.
In its electronegativity?
Not in its electronegativity. With helium, you can also place helium directly above beryllium. Hydrogen and helium's chemistries kind of float in both those categories. So you'll sometimes see a periodic table where you have hydrogen, helium, and then repeat hydrogen, helium on the other side. This is why in periodic tables that I've designed for a different room, hydrogen and helium are actually floated off of the periodic table because their chemistry is a little bit weird. Why is their chemistry weird?
So weird.
They only have one orbital really to access. That would be the 1s orbital, which can only hold 2 electrons. Every other element can hold multiple electrons through multiple orbitals, which changes the complexity of them. Since the vast majority of the chemistry that we deal with is outside of hydrogen and helium, we tend to focus on all the other ones and lose context of what's happening with our hydrogen and helium. So it's nice to float them off. I did not say that.
Well, wait. If it's in H2,
We'll push on this one a little bit harder because there's some more questions, it sounds like. What is the hybridization of that boron?
oh, sp2.
sp2, which means what's left over? A p orbital. How many electrons are in that p orbital? None, which means what could I put in that p orbital?
Electrons.
Electrons. The very first step of the reaction is that your pi bond shares with the boron. Since the boron is an electron acceptor, that's effectively our positive aligning with the negative of our alkene. The boron then is unhappy because it has exceeded the amount of electrons it's normally happy with, and it would eject the hydrogen. Is hydrogen a stable leaving group? No, because it is so unstable, it cannot just leave the molecule, it immediately reacts, thereby forcing the syn addition. I don't get a leaving group to have some time to spend its time floating around to come in and attack from the backside. It has to come in the exact same orientation. That exact same orientation is what's capitalized on in step 2, where we cleave off the boron with the peroxide, because it's still the same boron chemistry that's driving the reaction. Boron's a fun little molecule. If you really want to dig into it, you can. It's a wormhole. I don't recommend it.
So when the hydrogen leaves the boron,
The boron will be neutral.
no, the hydrogen,
When the hydrogen leaves
the boron.
the boron will be neutral because the hydrogen is leaving with electrons.
Okay.
The boron accepted electrons and then lost electrons. Stays
So the
neutral.
electrons go with the hydrogen.
Yep. Next question.
Question 4.
It was fun. I like talking about that.
Thank you.
It says hydro, so I'm already suspicious it's going to be this exact, yep.
Oh, I got this one.
Can you tell us the
Yeah, it is.
Okay, so when we talk through the chemistry, if you watch the lectures, and if you choose not to watch the lectures, you're getting it right here. That boron chemistry can be a bit challenging to deal with. Okay, focus on the primary chemistry. What does the boron act as? What is the hybridization of that boron? sp2, what is left over? An empty p orbital. What could you put into that empty p orbital? Electrons, which means that boron acted as an electron taker, okay, which would be an electrophile. Okay? The chemistry that we care about is the boron-hydrogen bond. We've now dropped so many electrons into that boron that it doesn't want those electrons, and so it shuttles the electrons out with our hydrogen. So our hydrogen effectively is a nucleophile, and our boron is effectively an electrophile. Okay? Why would I put those in parentheses and not actual names?
Because like officially, it's technically not.
It becomes weird to label a single molecule as both an electrophile and a nucleophile. In fact, so weird that we struggled with it when we did that question last week. Okay? So it only does one thing when we go through to run a particular reaction. In this particular scenario, it becomes very hard to label it as an electrophile and nucleophile. We can say what the arrows are doing, but we can't label the molecule as an electrophile. We can't label the molecule as a nucleophile either. Okay? What does the boron act primarily as? It's acting as an electrophile, and in particular, it's reacting with a pi bond. So our pi electrons come out and react, which then forces the hydrogen to come back and react to forming carbocation. Okay? What happens in our subsequent step? Well, actually, let's draw the result, I guess. We've got our new bond, new bond, hydrogen. Our last step involves sodium hydroxide and peroxide, and ultimately that's there just to get rid of the boron. You do not want the mechanism. So the end result is that we add H and OH across the pi bond. Okay? In that end result, it is a syn addition. We add the hydrogen and the OH to the same side of that pi bond. Okay? In that reaction, what did I say was here? Big red dot. What did I say was there?
Electrons.
Did I say there were electrons in that big red dot, or did I say there were electrons in the bond? What atom is that big red dot? If it was a proton or a carbon, did I specify it? No. Why not?
Not important.
Bingo. It's not important. The only thing that I care about is that boron to hydrogen bond. I can change the identity of the, we'll call it the green dot and the red dot. For those of you that were saying carbon, that's a fair point. I had that hanging bond. We could assume that was a carbon. Not what I was trying to do, but that's a fair answer. Okay. I don't care about what the green dot is or the red dot is. In the case of BH3, those are hydrogens, which means that molecule can do the reaction 3 times. Cool. Okay, which is nice because then I don't need as much of the reagent to go through and do the chemistry. That's neat. Okay, so what could the green dot and the red dot do? Okay, well, if that red dot was something that's really, 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 really big, and the green dot was something that was really, 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 really big, how would that change the chemistry of the boron hydrogen? Or would it not change it at all?
I mean, I suppose it really wouldn't change anything, right? I mean, wouldn't it make it just less reactive? So it's just not gonna do much once it's bigger? Right. Isn't something, the bigger something is, the
If
less reactive it is?
yeah, let's do this. Chemistry, if you're gonna hold a pencil, right? Right, you're holding that. Okay, you really just need two fingers, a thumb and a forefinger, right? Right. The other fingers may be playing a supporting role depending on how you hold the pencil. Right. Right. Mine usually play a supporting role, but let's just say you use your thumb and your forefinger, right? Right. That's the chemistry. That's the boron to hydrogen bond. What happens if I make my middle finger, that red bond, really, 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 really big? It is the size of this water bottle. Is that going to change how I write?
Yes.
Yes. Why?
Hard.
Ah, it gets in the way. So if we change the identity of that red or green thing, it could have a steric effect.
Oh, shit.
It could change the dynamics of how that molecule is able to react with whatever it's designed to react with. What if the red atom is really, 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 really electronegative? What is that going to do? It's going to pull the electrons towards it, which means what happens to the charge building on our hydrogen?
It lessens.
It lessens. And if it lessens, is it going to be as good as a quote-unquote nucleophile? No. So the identity of red and green can change and mutate the chemistry that we care about, that BH bond. Right? How does it change and mutate it? Now what you're asking is a graduate level class. We're not a graduate level class, so don't worry about it. Okay? All we care about is that it changes it. Why does that become important? If we go through and look at this is oh, I totally read it wrong with dicyamylborane. Right? And you may be like, I don't know what that is. So if that shows up on an exam, you're gonna be like, Mike, I don't know what that structure is. And what I will do is attempt to draw it for you, because I also don't really know what it is. What I would do is actually Google it, then draw it up on the board. And I think what's going to be obnoxious is they're going to draw something like that. And it'll be SIA2B-H. And I guarantee one of the questions that I would get was, what is SIA? Do you care?
Should I?
What's the chemistry we care about? The boron hydrogen bond. That's it. I don't give a flying rat monkey butt what SIA is. Okay, rat monkey butt. Okay, whatever. At least I didn't swear. Ish. Okay. All I care about is that core chemistry. Why did they add SIA to this? So, ooh, that's a fun answer. Like everybody's, just to mess with you. Ish. When we talked about reacting the boron reagent, what did we react it with? What did our BH3 reagent react with? We said BH3. What did it react with?
Pi bond?
Okay. Do better. Because if we go through and look at it, I didn't just react any old pi bond. What pi bond did we specifically react it with? An alkene. What are we reacting with it? You understood what I meant, maybe?
Yeah,
Now,
the alkyne.
is that an alkene anymore?
No.
No. Why did they change the boron reagent? It's no longer an alkene, which means we need to change the reagent so that it targets
The alkyne.
the alkyne. What's the chemistry? It's the BH. Exact same chemistry, but those pieces are altered because my starting material has altered. That's it. Don't stress at the stuff you don't know. Focus on the things you do know.
So then, for example, the BH3 wouldn't target the alkyne in this situation? If, say, if we reacted with...
So BH3 typically actually does not react well with alkynes.
Why?
It has to do with the chemistry of your boring and what's going on within those internal dynamics. So that is now graduate level class. We don't need to worry about that. Okay? Because you're now looking at detailed mechanism stuff that's beyond the scope of the class. Okay? So the chemistry here is BH. BH followed by, what's my reagent? The OH and peroxide. That looks really familiar. That's my reagent to do an addition to an alkene. What did I add in addition to my alkene? Okay, addition means what? Loss of pi bond and 2 sigma bonds. So when you say gain OH, you're giving me half the answer
And hydrogen.
and gain the hydrogen. So what should I do? I'll go look at my structure. I will take one of my pi bonds and I'm going to add an OH. And I'm going to add a hydrogen. What am I going to do to the rest of the molecules?
Nothing.
Nothing, because
Doesn't react.
nothing happened to them. And for the intrepid person that's following along, trying to put answers in, they draw this answer in, they're like, well, Mike, it's wrong. I know it's wrong. You didn't let me finish. What functional group is that?
Ketones or a
Carboxyl.
It's not a carboxyl,
Yeah.
because a carboxyl would be something more along the lines of that, okay, which is not an alcohol or a carbonyl, but when I put those two functional groups near each other, they become our carboxylic acid. Okay, here I've got an alcohol that I put next to an alkene. Do those chemistries affect each other? Yes, so much so it creates a new functional group. That new functional group happens to be called an enol. And what should I know about enols? They tautomerize. They tautomerize to... That's a fair statement. The ketone. All right, all right. I think I lost a carbon. Did I lose a carbon? I lost a carbon.
Oh shit. I mean, I remember watching lectures of this stuff, it just never came up. Well, here
Which,
it
the
is.
ketoenol? Yeah, it shows up real briefly in 7, and you're like, why are we talking about this? This is kind of irrelevant. It shows up here, and it'll show up a lot next semester. If you don't have to take next semester, you don't have to worry about it, except that it shows up a lot in biochem if you were actually taught the chemistry side of biochem. If you're taught the bio side of it, you don't need to worry about it. Okay? So this reaction tautomerizes to drop in the ketone. Okay? What could you do? You could try and memorize this. Okay? But then what's going to happen is they won't use dicyamyl. They'll use some other goofy thing. Because I can change the identity of those things willy-nilly. And it will change the targeting effect of the BH bond.
Well, how will we know the effect? How do we know it didn't just...
How do I know that I keep saying it that way, dicyamylborane focuses on triple bonds? You don't need to. Okay? Why do you not need to? How many of you are going to become a synthetic chemist? There's your answer. If you're going to become a synthetic chemist, then you need to memorize the reagent to every single reaction. Okay? If you're in anybody else's class, do you need to memorize it? Possibly. But my focus has always been on what is the chemistry behind it. That is purely memorization. So I will ask it in a way that focuses on, did you learn the chemistry or did you focus on memorization? Believe it or not, both will lead you to the correct answer. So you get the option to do either path. But if you focused on the chemistry, you had to memorize less. I would argue you had to work less hard to get that same information. And I think more importantly, the content you learned, how you approach the content, is now so drastically different that you can use OChem in your biochem class. You can use OChem in your other classes. I've got another student from a different semester who's come back and been like, Yeah, I've noticed that I've stopped taking notes in my classes because I just sit there and listen to how they're putting things together, and I pay attention to how the pieces move, and now I understand it. Like, I always took tons and tons of notes, but now all of a sudden things have shifted because you asked me to look at the content of what's happening, not at the facts. Make no mistakes, that is hard. And that is by far an exception to the rule. Okay? But if you can make that shift, it can help you further down the line. But it requires that you make that shift, and you have to commit. Yay. With that, we're done. Or actually, you know, with that, you all can do great things. I have every confidence that you can, but you do have to make an intentional shift in how you approach the content to either match what I'm doing or to completely ignore me. Those are really your two options. I'll get angry about the other one, but as long as you get things right, there's nothing I can do about it.
We should go